this computer. Okay, I hit record. All right, so this past week, the set that I chose are number theory things. I see that both Jana and Luke had done 3 problems, and also Luke tried the last problem. I'll bug you about it to find out what you did a little bit later on when we talk about that problem. And of course, Joseph did all 5 of the problems, and well, these problems should not pose as much of a challenge, although for some reason it took him a few tries to do some of these problems. All right, so this set is about number theory. The first 2 or 3 problems are about prime numbers, prime factorizations, and then the last 2 are maybe something a little bit different. So let's get to it. Okay, the first one, I think everybody, I guess Jana and Luke did know. I don't know if you look at the problems or not. Anyway, so there's a bit of a story about hash tables. It doesn't really matter what the story is, but the most important thing is what is it that they're asking you? Okay, they ask you that the inputs is a sequence of 1,000 table sizes. Each is a number from anywhere between 2 to 2 to the 30th minus 1. It's strictly less than 2 to the power 30. N of input is indicated by n equals 0, which should not be processed. I will put the smallest prime number larger than 2n. Also, if n happens not to be prime, add the parenthetical notes that n is not prime. So, for example, 29, if you double it, is 58. 58 is, of course, not prime. So you want the next smallest prime, and in this case, 59 is the next smallest number that also happens to be prime. You always want a number that is larger than 2n. So even, well, 2n can never be prime because it's 2 times something. So the first prime that you can possibly have is 2n plus 1. And then also, in this case, 33, it turns out that 2n plus 1 is prime. So you get it right away, but because 33 itself is not prime, you also produce this number. You also produce a statement that 33 is not prime. So basically, this is a primality testing problem, right? You're given a bunch of numbers. Sorry, you're given a number. Then you're going to look for 2n. You're going to see if 2n plus 1 is prime. If it is, you're done. If 2n plus 1 is not prime, then you have to try the next one, the next one, the next one. And the hope is that this is fast enough. Also, the number that they gave you, you have to check if it's prime or not. And you have 1 second to do it for up to 1,000 cases. Okay, so that's the problem. So since I have 2 people here that have done it, maybe I ask the 2 of you to tell us what you've done, how you did it. So who do I start with first? Let's start with Luke first.
So I basically get my number n, and then I double it, and then then I have a function that's is prime, just returns true or false. Then I say while not is prime, and then I just increment n till I find the prime number, and then I just output that.
So basically brute force.
Yeah.
Okay, now Jana, you already sent me the code, so I know that what you did, and it's essentially the same thing, correct?
Yeah, except I only check the odd numbers.
Right. Okay, so basically then the question is, can you figure out how to do primality testing? If you can, you're kind of mostly there. So basically you want to write a function, bool is prime int n, and then somehow this will return true or false if the number is prime or not, right? And now there's a number of things that you have to worry about. How big can this number be? What is the size of the input? Well, the original n, it's between 2 and 2 to the 30. Okay, strictly less than 2 to the 30. But but you're not going to be testing the original input. You're going to be testing the original input 2n plus 1, 2n plus 2. Well, there's no reason to do 2n plus 2 because 2n plus 2 is divisible by 2, and so on. So when you multiply these by 2, this is going to be somewhere between 5 and 2 to the 31 or so. Okay, roughly. Okay, so this is going to be big because 2 to the 31, 2 to the 31 minus 1 is in SMAX. If you're using 32-bit signed integer, 2 to the 31 minus 1 is the largest you can have. So when you do 2n plus 1, it's okay. But when you do 2n plus 3, 2n plus 5, you might actually blow up this. So immediately, you should probably cross this out and use long, long. Now, you might be saying, oh, it's probably okay if I use unsigned integer, because unsigned integer, I can go up to 2 to the 32 minus 1. And you're right. But we might as well just use 64-bit integers to be absolutely safe. Okay? There's no real penalty for going to 64 bits. There's a little bit of speed difference, of course, but it's not usually a determining factor of whether your program is going to run too long or not. So that's the first thing. And then the second part is, well, how do you decide if a number is prime? Okay, so how do you decide if a number is prime? Okay, either Luke or Janet, since you've done it, you want to share how you decide if a number is prime?
You can use a sieve.
Okay, so you can use a sieve. What does that mean?
Basically, you go through and then like each prime number, you find all the multiples of it, and you say that those multiples are not prime.
Okay, let me do the sieve by hand first. Okay, we'll just do 30 numbers, so I don't have to write so much. So the idea of a sieve is that, okay, 1 is never a prime. Okay, so then you start from the beginning. So you say 2. 2 is not crossed out as prime. Now that you found a prime, you go and cross out all the multiples of 2. So cross out 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay? So none of those can be primes because they're divisible by 2. Then you go circle 3, because that's the next number that hasn't been crossed out. And now you go and cross out all the multiples of 3s that haven't already been crossed out. Okay. 4 is already crossed out, so you skip it. 5. Then you go and cross out all the multiples of 5 that hasn't been crossed out. And then 7. And then by this point, all the multiples of 7 have already been crossed out, and so on and so forth. So these are all the primes left. Okay. And I'll show you later how you write this code. The idea is that with a sieve, you basically have a Boolean array for one for each number that you care about, and you go and cross out all the multiples of 2s, 3s, 5, 7, etc., etc. And then when you finish crossing them out, whatever is left behind, those are the primes. Right? And I guess if you have a sieve and you want to know if a particular number is prime, well, if you want to know if 23 is prime, you just look into the Boolean array that's represent a sieve, and it's either true or false, whether you have crossed it out or not. And you look at, I don't know, 20, you look at 27, it's been crossed out, so you know it's not prime. That's the idea. And the sieve is very good if you want to find what is a sieve good for? Find all primes up to a certain number, m, whatever m is. And the complexity, it's capital O of m log m. In other words, it's really fast. Up to, so basically if you have an array of size m, if you're interested in up to m numbers, then it's m times a relatively small factor. Log of m is already small, log m is even smaller. Does it work? Does it work for this problem? Okay. It turns out that this doesn't work in this problem because you are interested in numbers as big as possibly this much. Okay. And if you're interested in numbers possibly as big as this much, then this is going to be your m. And your complexity is going to be m times log m. Log m is nothing, but just the m is going to kill you. But in fact, your program probably won't even run. It's not just that it doesn't run in time, it probably doesn't run because you need to allocate an array, a Boolean array, for storing this many entries, and it probably will run out of memory, right? 2 to the 30, even if you decide to pack everything so that each element is 1 bit instead of 1 byte. Okay, by default is 1 byte per element. If you do 1 byte, this is like what, a gigabyte, 2 gigabytes or something like that of memory just for this array, which is too much. Okay, so a sieve in this case doesn't completely work the way that is described. Does that make sense? Yep. Okay, now we'll come back to this sieve later. So what other things do you know? Okay, well, the other thing that you know, and this is the really simple thing that you probably learn when you learn your in your first programming course, you probably have this idea that you can just try dividing by 2, 3, 4, 5 until and see if anything divides other than the one in itself. And if nothing divides, then it's a prime. Otherwise, it's not a prime. So a very simple thing that you can do is you can just say for int some trial divisor d, and then I'll just say d plus plus. If n%d is equal to 0, so in other words, I found a divisor of n, then I return false. If I go through this loop and I haven't found a divisor, I return true. The question is, what do you put in here? When do you stop looking for divisors? And sorry, say that again.
Square root of n.
Okay, so what should I write down? D
is less than or equal to the square root of n.
Like that. Okay, so d is less than equal to square root of n. Now this, it's not the greatest thing to do because n is an integer, or a long, but some kind of integer type, and square root gives you a floating point number. And floating point numbers, it's subject to rounding errors. So this is not the greatest thing to do. So instead, instead of saying let d is less than equal to square root of n, it's better to square both sides and say something like this. That way, both sides are integer values, so there's no possibility of round of error. And then the other thing that this is wrong, and I think Jana has seen this before, is that this has to be long, because otherwise the d times d here can overflow. And if d is large enough, then d times d can get negative. And then this n will never, this will always be true. And in particular, if n is 2 to the 31 minus 1, basically the ins max, 2 to the 31 minus 1, then this one, no matter what value b is, it will always be less than or equal to n, because by definition, ins max is the maximum possible integer. So even if b is really big, this will just overflow, give you something negative, and then this will just run forever. And this is what I believe Jenna had with her runtime limits. Time limit exceeded in the first try. It's because of the overflow. So it runs in an infinite loop. So this is a common thing to common trap to fall into. So make sure that you use long. And how long does it take? Well, it takes exactly square root of n step. Well, not exactly, but at most square root of n steps. Okay, which in this case, it's apparently good enough because n is 2 to the 31. So square root of n is approximately 2 to the 15, somewhere between 2 to the 15 to 2 to the 16, which is about 60,000. And that's not very much. What other things can you do? You can, if you want, separately check if n. So if you can separately check that if n is divisible by 2 and n is greater than 2, then return false. Okay, so if it's divisible by 2 and it's bigger than 2, you can quit right away. Why do I do that? Because then I can check only starting from 3, and I know that all the divisors that are useful to check are odd. I don't have to check 4, 5, and so on. That would cut down the checking time by half. If you really want to be faster, you can check only the prime numbers instead of trying all the odd numbers, but then you have to get all the primes to begin with. But how many primes do you need? You only need primes up to square root of this, square root up to the 31. So you only need to know the primes up to about 60,000 or so. And that, if you want, you can generate that list of primes using a CIF, because this is relatively small. Does that make sense?
So the fastest way is still brute force then. We should just use a sieve first to get the primes and then
Yeah,
brute force through the primes.
Yeah, so I'll just show
Okay.
you my solution. Okay, so the first part is not very interesting. There's an init which computes all the primes that I need with a CIF, and then I solve all the cases. So what do I do with my CIF? So as I said, you only need up to 60,000, 65,000 or whatever, but I just made it into 100,000. Doesn't really matter too much. Then I have a CIF. Okay. At the beginning, I so this set everything to be false, and then I set everything to be true except 0 and 1. Then my CIF goes like this. So this is the standard way of writing CIF. So you loop all the entries in the CIF. If I already marked it as false, then I don't do anything. So if I already marked it as false, then that's it. There's nothing to do. Otherwise, I have to mark all the multiples. And the way to do it is you have a loop that takes j, and you can actually start with I squared. So let me explain to you later why I started I squared. But basically, you start somewhere, then you mark up all the multiples of I. So all of them set to false. And then this primes dot pushback, this is just a vector of all the primes that are collected so far. And then why do I need this vector prime? Because it's prime, basically. Okay, so the first thing is if the number that you give me is already part of the CIF, I just read it off. I don't have to do any division. Otherwise, I check all my primes. So I go through all my primes from smallest to largest. If the prime is bigger than square root of n, then I'm done. So it's a prime. Otherwise, I see if it's divisible by p, and if it's divisible by p, I say it's false. And this assert false basically means that if it ever executes this line, your program will crash. And it's just a sanity check for me because I know conceptually that I should always exit this loop either because of this or because of this. So if I have a bug, then I might somehow fall into here. And then my main code, I start with 2n plus 1. And while it is not prime, I just keep on adding 2. And then at the end, I ask, is the number that you give me a prime? And if so if it's not a prime, then I print out this extra statement that says that the input is not a prime. Okay, so that's my code. Now let's go back to this part. Then many people, if they're not writing things, maybe they're writing this for the first time. Instead of I times I, they might say 2 times I. Okay, so what's going on? 1, 2, 3, 4. So this is my step. (19, 20, 21, 22, 23, 24, 25, 6, 27, 28. Okay, so I'm going to cross out. Okay, 1 is never a prime. Then I'm going to circle 2, and I'm going to start at 4 because 4 is 2 times 2, and I'm going to cross out all the multiples of 2. Okay, so this is nothing that new. Now I get to 3, and I'm going to start crossing out multiples of 3. And if I start at the next multiple of 3, you might say, well, I'm going to start at 6, 9, 12, and so on. But 6 is already crossed out. So I can start at 9, okay? 9, 15, 18, 21, 24, 27, and so on. Then I go to 5, and you might say, well, I need to start by 10, 15, 20, 25, 30, etc. But notice that 10 has been crossed, 15 has been crossed, 20 has been crossed, and the next one that you actually have to cross is 5 squared, which is 25. And it turns out that anything, so when you're at I, when the prime is I, 2i, 3i, 4i, 5i, whatever, up to I minus 1 times I, all of these have been crossed out already. And the next one that you have to cross out is I times I. Why is that true? Because 2 times I, it's also a multiple of 2. So if 2 times I is also a multiple of 2, it has already been crossed out when you look at 2. 3 times I has already been crossed out when you look at multiple of 3s. 4 times I, well, 4 times I is actually a multiple of 2, so they have already been crossed out, and so on. So the first one that you actually have to look at is I times I. And if you do this, if you do it this way, then the complexity is n log n. If you didn't use this trick and you say, well, I'm going to start at 2i. So even though some may already have been crossed, you start there. If you do that, the complexity is also not so bad, but it's a little bit worse. Okay, it's probably good enough anyway. Log n and log n is not that much of a big difference, but it is a little bit less optimal. In any case, once you're used to doing stiff, it doesn't actually cost you any more or less time to do I squared, to start at I squared instead of 2 times I. So you might as well do that. Okay. The only other thing that you have to always remember when you play with numbers that are big is to make sure that you use a data type that doesn't have overflow based on your problem. So always watch for that. Okay. Any questions about this one? Is it all good?
Yep.
All right. Now, prime reduction, I believe both of you also did, yeah? Yes. Okay, so prime reduction, what is prime reduction? Okay, so a prime number is, it's an integer which is even if divisible by only two integers, I and P. A composite integer which is not prime. Fundamental theorem says that any integer x can be expressed uniquely as a set of prime factors. So for example, 10 is 2 times 5, 16 is 2 times 2 times 2 times 2 times 2, 231 is this, and blah, blah, blah. So now they give you a process, which they call prime reduction. You're given an input x. If x is a prime, print x and stop. Otherwise, factor x into its prime factors, p1, p2 up to pk. And these, okay, one of the things that you have to know is that these pi's are not distinct, may not be distinct. So if you have 16, if you're factoring 16, then you have 4 factors, they have all 2's. Then you let the new x become the sum of the factors, and then go back to step 1. So you keep doing that until you get a prime number and stop. Input consists of up to 20,000 integers, 1 per line. Range is between 2 and 1 billion. The number 4 will not be included in the sequence. Try to see why it's excluded. So why? Because if you have 4, then 4 is equal to 2 times 2. So you add the 2 factors together, you get 4 back, and then you basically run into infinite loop. Input ends with a line containing only the number 4. For each integer, print the value produced by the prime reduction executed on that input, followed by the number of times the first line of the process is executed. So basically, you just have to simulate this process. There's not a lot to do. The only thing that you really have to know is how to factor. Okay, if you know how to factor, you're done. And factoring, this is up to 1 billion. So again, when you do, you can do things by brute force because you only have to check for divisors up to the square root of that, which is not that much. It's about 10,000 or so, or 30,000. So it's not that much. So, okay, there's not too much to say. So I'm just going to go straight into the code. So I have my solve function. You take an input n, and then I have a counter that keeps track of how many times I execute the first line. Next is basically the x value that I'm keeping track of. And step n. So step n does exactly one step here. It takes a number, factors it into the prime factors, and add them. And the only time, as long as the number is not 4, the only time where a number, when I go through this process, give me exactly the same number as I started with is if the number is prime. Okay, so if a number is prime, then when I do the prime factors, I'll just get one of them. When I add them up, then I get itself back. So I'm using this test to say that if the number that I have is exactly the output of step, then it means that the number is prime. So this is basically all that's going on. It takes the number, do one step. Remember what the number of times is by 1, increment it. While these two things are not the same, meaning that it's not prime, I basically move things along by 1 step. So n is now next. Compute the next step. Count the number of times by 1. So then the only tricky part, I suppose, is how to factor. And really, here it is. So answer is the sum of all the factors. And here I'm trying all the divisors from 2 all the way up to square root of n. Okay, I'm not even gonna, I didn't even bother separating out the even and odd ones. So I just try all of them. Again, make sure that you use long. Okay. And then now if it's divisible by 2, 4, 2, 3, whatever it is, here I'm using a while loop because I could I could divide by 2 multiple times. I could divide by 3 more than once. So wow is divisible by p. I add one more p to the answer, the sum of the factors, and I divide the number by p. Okay. So whenever I find a divisor, this n actually gets smaller, which will allow you to actually terminate this loop a little bit faster, possible. Now, the other thing is when you exit this loop, n may not be 1. N could be bigger than 1. So for example, if you have something like, let's see, 15, for example. So if n is 15, then you try p equals to 2, nothing happens. You try p equals to 3, then of course when you divide out the 3, n becomes 5. And then p is the next loop, p is equal to 5, but 5 times 5, p squared is 25, which is greater than n, which is 5. So this loop actually exits, and n remains 5. So when you exit, it's possible that n is actually greater than 1, and whatever is left over is the last prime factor. So you have to consider that as well. So this is one thing that many people, when they first start writing brute force factoring, they forget, is that they think that once they exit the loop, they're done, but they might have one last factor to deal with. Okay. Apart from that, this one is fairly straightforward. Are there any questions? Is that more or less how you guys did it, Luke and Jana?
Yeah, that's how
pretty
I
much.
did it.
Okay. Okay. So that's the second problem. Relatives. Okay. Let's read the problem and then we'll discuss this. Okay, given n are positive integers, how many positive integers less than n are relatively prime to n? Okay, if you've never heard of this word relatively prime, what does that mean? Two integers a and b are relatively prime if there are no integers x greater than t or equal to 2, y and z greater than or equal to 1, such that a is equals to x times y and b is equals to x times z. What the heck is it talking about? It's saying that x is a common factor of a and b. And it's saying that there are no common factors bigger than or equal to 2. In other words, another way to say that two integers are relatively prime is if the greatest common divisors of a and b, it's 1. Okay, they have no common factor. That's what relatively prime means. Now, I don't know, have you heard of this word before, relatively prime? I don't know which course you might hear from.
Yeah, I've
1820?
heard. I took number theory, so I've heard
Oh,
that.
okay, then you know for sure. Okay, well, if you know number theory, if you took number theory, then you probably are done already. Okay, so let's see here. There are up to 10 test cases. Each case input has the number n that's between 1 and 1 billion. Okay, 1 billion, 10 to the 9. And for each test case, there should be a single line outputting the answer to the question posed above. So let's maybe ask a few questions. So if you have taken number theory, maybe you already know these answers, but let's see. Okay, so the first thing that you might say is, well, how do you compute GCD of A and B? You give me two numbers, A and B. How do you get the GCD of A and B? And this, you should have seen this in possibly 1820, and if not, maybe other courses like Math 2000. It's called a Euclidean algorithm. And the idea, let's just, should I just write some? So maybe I'll just write it in recursive form. If A is let's say if B is 0, so if B is 0, then GCD of A and B is equals to A. Doesn't matter if A is 0 or not. If A is 0 as well, then GCD is 0. If A is non-zero, then GCD is A. If B is greater than 0, okay, so here, assume A and B are greater than, so there are no negative numbers. You can do negative numbers too, but let's not worry about that here. If B is greater than 0, then the answer is the GCD of A and B is the GCD of B and A mod B. Okay, so for example, if I have A is, I don't know, 36 and B is 24, then GCD of 36 and 24 is the same thing as GCD of 24 and the remainder of A divided by B, which is 12. And then you can keep doing this, right? Then you can say, well, okay, then this is a GCD of 12 and the remainder of 24 divided by 12, which is 0. And then now that one of them is 0, GCD is 12. Have you seen this before?
Yep.
Okay. And the Euclidean algorithm, how fast is it? How slow, how fast? It's, I don't know if you've seen this before, but basically it's log 2 of the maximum of A and B. So you take the figure of the two numbers, take the log of base 2, that's how many steps it takes. So for example, if you have a number that's up, so if your numbers are up to 2 to the, so a billion is basically, oops, what did I just do? Sorry. Okay, so a billion, whoops, why is my pen reset? Okay, so by a billion, it's about 2 to the 30. So then if A and B are up to 2 to 30, then this would take about 30 steps. Okay, so that's what you can do, use the Euclidean algorithm. My whiteboard thing crashed. Okay, so now you might say, okay, so what about this problem? The problem says, given n, how many number less than n is relatively prime to n? And you might say, so here's a simple problem way of doing it. For int I equal to 1, I less than n, I plus plus. You don't have to check n because it's n, it's guaranteed to be not relatively prime with itself. Then you say, well, if GCD of I and n is equals to 1, answer plus plus. Right? This will do it. The problem is that even though each call of GCD is fast, if n is big, then this loop, even if you're doing almost nothing in the loop, you're doing a little bit, but even if you do nothing in this loop is already executing too many times. It's too slow. Okay? So doing it sort of brute force will not help. And then at this point, either you already know what the answer is because you took number theory, or you may start to think, okay, are there any special cases of n where you know the answers easily? So for example, when you look at these numbers that you look about relatively prime and so on, you might want to look at the way it factors. So what is the way, how can n factors into prime factors? So the simplest way is if n is prime. Okay, so what if n is prime? Well, if n is prime, then everything, if n is prime, then all of these numbers from 2 all the way to n minus 1 cannot have a common factor with n, because n, it's not divisible by any of these things. So in that case, if n is prime, everything in this range has the common factor of 1 with n, because there's no common factors at all. So the answer, if n is prime, if n is equals to p for some prime, then the answer is p minus 1. Now the next simplest case is if n is some power. So it's got p to the alpha. So some power prime. So if you look at all of these numbers up to p to the alpha, the only times that you can have a common factor is for you see other powers of prime. These are the only ones that can have a prime, that can have a common factor with p to the alpha. Nothing else can have a common factor. Wait, what am I trying to say? That's not true. Sorry. I messed up something. I mean, what I meant is 2p, 3p, all the multiples of p's. Okay, anything that has a multiple of p can have a common factor with p to the alpha. But nothing else, if it's not a multiple of the prime, it cannot have a common factor with this, because nothing else, no other prime factors divides p to the alpha. So then you say, well, how many multiples of p's there are? Well, it's p to the alpha. So the total, it's p to the alpha, and the total number of multiples of p's is that number divided by p. Or you can write p alpha minus p to the alpha minus 1. Okay, well, what about something more complicated? So what, for example, maybe you have your product of 2 primes. So the 2 prime powers. Now this is where things get a lot harder, and then you may or may not see this. You might have to experiment with it, and then maybe eventually, or maybe you just looked it up or you know this fact, somehow the answer is the answer for P1, the answer for this chunk times the answer for this chunk. And in general, if you have a prime factorization of a number into prime powers, you basically solve the prime power, each prime power separately, and then you multiply by the answers of each prime power factor. And this, actually, there's a name for this in number theory. It's sometimes called the Euler phi function. Or some other people also call it Euler-Todian function. And it's a well-known number theory function, basically, that if you know how to factor a number into the prime powers, then you just apply this formula and that's your answer. So here, I guess it's a little bit more than just, can you do this? Can you figure this out by yourself? But also it would help if you have some knowledge of what's going on. So in number theory, Euler-Todian function counts the positive integers up to a given integer n that are relatively prime to n. So this is basically exactly what you're asked to do. It says Euler-Todian function is a multiplicative function, meaning that if 2 numbers m and n are relatively prime, then computing the phi of m times n is exactly the same as phi of m times phi of n, and so on. And then, what did Euler phi. Okay, so this is the formula that I show you, right? And then multiply, and this is more or less the final thing. If n is a product of these prime powers, then the final answer is this. So I don't know if this is a very interesting problem in the sense that either you know it or you don't, I suppose, or maybe you can try to figure this out. If you do, then it's really not that hard, especially because in my code library, there's a file called Euler Phi. And so that's all I did. I just copy and pasted the code, and then I just call it. So, you know, if you've taken number theory or if you have read up on number theory, of course, then knowing some of these things would be useful. Okay, and in the code library, there are plenty of number theory stuff, and this is sort of the first one. Okay, any questions? So for those of you, I guess Luke and Jana, you both did it. Did you write your own or did you copy this code?
I just wrote my own Euler
Okay.
function.
I wrote my own too.
Okay. Yeah, it doesn't hurt to write your own, but you also realize that it is available here. Probably this is written in a funny way that you don't know what's going on. Maybe you don't know exactly what's going on here. This is basically exponentiation with the fast exponentiation that says if the exponent is even, then you square it instead of multiplying and so on. Anyway, all right. Now the last two are more interesting, perhaps, because nobody here has solved it yet. So let's look at these last two problems. Oh, wait, before I go on, I see a couple more people joining. Blake and Danielle, welcome.
Thank you.
Yeah, so we're just talking about this week's problem sets. And if you missed, I don't know exactly when you joined, but if you missed any of this, I always have the recording posted later. So just watch Discord out. They'll have a YouTube link. And then, of course, you're always welcome to ask me questions, private message, and so on. Okay, anyway, so lower order zero. So this one, it's a little bit different, maybe, compared to the previous ones. So let's see. When you compute a large factorial number, it has a long string of lower order zeros at the end. This makes sense because every time you multiply it in something like 10 or 20, you're sure to pick up another lower order zero. Okay, so every time you multiply it 5 or 10, 20, 30, whatever, you might get another zero. Thus, it's easy to guess the low order digit of something like 3,249 factorial, because the answer is probably 0. The answer is 0, the last digit. However, it is a little harder to guess what the lowest order non-zero digit will be. Write a program to do that. Okay, so input consists of up to 1,000 test cases. Each test case has a single positive integer I, less than or equal to 1 million. Input ends with a value of 0. For each test case, print out the value of the rightmost lowest order non-zero digit of I factorial. So 3 factorial is 6. So no problem, 6. 25 factorial. What is 25 factorial? Well, it's a little bit hard to figure out, I guess. Let's see if, so I'm going to cheat. So on our machines, this is on the university machines, there's Maple, you can actually compute 25 factorial, and it will give you this number. This is probably gonna, so to the 32 minus 1, that's the largest integer, unsigned 32-bit integers. The largest unsigned 24-bit, 64-bit integers. It's this much. So basically, you cannot compute 25 factorial even with 64-bit integers. Okay, you have to somehow, if you were to compute 25 factorial, you realize that there's a bunch of zeros at the end. You don't care about that. And the last non-zero digit is 4, which is the correct answer here. Of course, 25 factorial is nothing because you're supposed to compute up to a million factorial. So if I were to do 492 factorial, I don't even know. Oh, it will actually compute it. And the last non-zero digit is 8. So 1 million. Okay, it's easier if I do this. What just happened? Oh, hang on. The 6, the factorial goes with the 6. Okay, so, oh, I guess it computed it, but it decides that it cannot possibly show it to you. Okay, anyway, this is Maple. It allows arbitrary precision integers easily, but we don't have access to that. Okay, so what are we going to do? How are we going to get the last non-zero digit of n factorial? Does anybody have any ideas, any kind of intuition or guesses on what you should even try?
I did try where you just find like, so 2 is obviously 2, and then we can go 2 times 3, and that's 6, and then 6 times 4, and then you kind of just keep modding by 10 until you get a number that isn't 0 each
Okay, so-
time. But
So
that
if you
took
just
too
want to
long.
know, if you just want to know what is the last digit of any calculation, doesn't really matter if it is a factorial or whatever it is. If you just want to know the last digit of any calculations, in this case, the calculations could be written as 1 times, 2 times, 3 times, up to n, but doesn't matter what it is, then you can basically do the calculations, all the steps, mod 10. Every step along the way, you just do %10 at every step, and then eventually you will get, once you finish the calculations, you will get the last digit. Now that doesn't work here because the last digit for most input is probably 0, and you will get 0. But that doesn't help you because you don't want the last digit, you want last non-zero digit. So if I have a number, whatever that number is, I don't know, doesn't even have to be factorial. Okay, if I want to get the last non-zero digit of this number, what do I have to do? Well, first I have to know how many zeros there are. If I know how many zeros there are, in this case 6 of them, I would do n divided by 10 to the 6. Okay, and then I would do %10, because n divided by 10 to the 6 will get rid of these ones, and then when I do mod 10, I will grab the last non-zero digit. Does that make sense? If that makes sense, if somebody magically told you that there are exactly 6 zeros at the end, then you're done. So the question is, how do you know how many zeros there are at the end? Okay, of n factorial. So you have n factorial. It doesn't actually matter. It doesn't really matter what n. This is n factorial. You have some kind of expression, some kind of calculations, and the point is that after you do a bunch of calculations, the answer is going to be something that doesn't have zeros times 10, doesn't have n to the 0 times 10 to the something. And the question is, what is this? How can you get a handle of 10 to something? Well, 10 is 2 times 5. So if you have a 10 to the something, that's the same thing as saying that you have 2 to the something times 5 to the something. So in fact, if you look at n factorial, let's say you look at a million factorial, doesn't really matter, and you realize that you have when you factor n factorial, you have 2 to the something. I don't know what it might be. Let's say 900. I'm just making numbers up. Maybe 3 to the, I don't know, 600, and 5 to the 450. Okay, and then maybe a bunch of other things. The only way you can get zeros at the end, it's through combinations of 2s and 5s. None of the other numbers can contribute to this 10 here. Does it make sense?
Yeah.
Okay, so if you believe me, then how many 10s, how many zeros can there be? You look at the minimum of these two exponents, and you realize there's the 10 to the 450 by crossing out this much and then reducing this exponent to this much. And if you follow this, that means if you knew that this n factorial factors in this way, then you know that there are exactly this many zeros, 450 zeros at the end, and then the rest are guaranteed to produce non-zero in the last digit. So you can just remove this and then multiply all of these things mod 10. And that would be your answer. Okay, so again, if I somehow manage to get n factorial, it's, I don't know, we'll just make up some number. And so on. So let's say that you get some kind of prime factorization for n factorial. And then you just basically look at this and say, well, look at 2, look at 5, the exponents. That means I can take out this much, this many zeros at the end. Once I took these out, none of these other numbers, when you multiply them to each other, can introduce another zeros at the end. And so you just multiply all of these things mod 10, and that's the answer. Assuming, of course, you know how to factor n factorial. Does that make sense?
Yep.
So now the question is, how do you factor n factorial? Does anybody know how to factor n factorial? Okay. So there are a few things that we should think about. If I have a number n is equals to the product of two numbers a and b, what you should not do is to multiply these two numbers, get a bigger number, then factor them, then factor it again. What you should do is factor a and then factor b, because they're smaller, it's easier to factor. And once you have the factor of the two numbers, you can then just basically put the factors together, right? If this is 2 times 3 and this is 3 times 5 squared, then you don't have to multiply it all and factor it all over again. You know that it's 2 times 3 squared times 5 squared, right? If basically you're already given kind of a partial factorization. A and b might not be prime, so you have to break them down further, but you don't want to multiply them together just so that you can break, spend some time to break them up again. So that's the first observation is, if you already have a product of individual things, you factor each one individually. That's easier. So why do I talk about this? Because I know that n is the product of a bunch of things. So if I can factor all the numbers from 1 to n, then I can just throw them together. I don't have to multiply them all out and then factor them, right? I can just factor each one individually and then put it together. Now, let's say, okay, I want to know, so sorry, not n factorial. It's 1 times 2 times up to n. So now I want to know n factorial equals to 2 raised to some power, 3 raised to some other power, 5 raised to some other power, and so on, right? I want to get the prime factorization. I want to know how many times, how many powers of 2s I have, how many powers of 3s, how many powers of 5. So let's just look at powers of 2s. How many powers of 2s are there? Okay, I'm writing this again because I want to make it a little bit bigger and to illustrate my point. Okay, that's good enough for now. Okay, so how many powers of 2s are in this product? Well, there's a 2 to the 1 here. But everybody, so now that I see that there's 2 to the 1 here, actually everybody that's a multiple of 2 has the 2 to the 1. Okay, each multiple of 2 has at least 1 2s. Okay, so there are 8 of them here. But that's not all the powers of 2s because I have 4s too. All the multiples of 4s have another one. Okay, now I know that this is each multiple of 4 has 2 powers that I have to count, but I already counted the first power in the multiple of 2, so I don't have to count them again. So far, I have 12. Okay, but that's not all. Multiples of 8, there are 2 of those. Multiple of 16, there's actually 1 of those only. So altogether, if I look at 16 factorial, it's 2 to the 15 times 3 to the something times 5 to the something, and so on. I can figure out the power of 2s is 15 by looking at this. This is kind of like a sieve, right? I look at 2 and then I look at all multiples of 2. I look at all multiples of 4, 8, 16. Every multiple of 2 gives me a 1 power of 2. Every multiple of 4 gives me another power, any power of 2. Every multiple of 8 gives me another power of 2. Every multiple of 16, 32, etc. Of course, if n is 16, there's no reason to look at 2 to the 3, 2 to the 5, 2 to the 6, and so on. But in general, you basically look at all the multiples of different powers of 2s. And there's nothing magical about powers of 2s. If you're looking at 3s, it's the same idea. How many multiples of 3s are there? How many multiples of 9 are there? And so on. So in general, if I want to know how many multiples of a certain prime it's in the factorization of n factorial, the formula to compute that is this. N divided by p, rounded down, that's the multiple of p, the number of multiples of p. But that's not all. The number of multiples of p squared, number of multiples of p cubed, p to the 4th, and so on. Eventually, p to the some power, it's going to be bigger than n. In that case, all those values, when you say n divided by p to that power, floor will be 0, and then you stop. And the number of terms that are non-zero, it's exactly log of n to the base p. Well, let's say, I don't remember it's for stealing, but maybe I shouldn't use the word exactly. Let's just say about. It's that many terms. So it's relatively simple, relatively fast to compute, because when p is 2 and n is 1,000,000, then p is at most log of p to the log of n to the base p is at most 20. And if p is bigger, if you use bigger primes, then this is even smaller. So you can easily compute the number of times the power of prime p divides into n factorial with this formula. And it's basically a sieve. Sort of the same idea as a sieve. And I'll show you the code later on how to compute this. So if you can do this, then the problem becomes very simple, because once you know, whatever all these exponents are, right, all of them, how many primes do you have to go to? Well, you have to go up to all the primes up to n. So all primes less than equal to n, because they can all be appearing in n factorial. And then basically you'd say alpha 1 and alpha 3, it's actually guaranteed that alpha 1 is bigger than or equal to alpha 3. So when you try to remove powers of 10s to get rid of the trailing digits, you can actually just get rid of this. And then you would say this is now alpha 1 minus alpha 3, keep the other exponents unchanged. And then you just multiply all of these things mod 10. And that's it. That's the answer. So let me show you my code. Okay, so I have an initialization function, which is basically a sieve that computes all the primes up to, I believe, 1 million. And then I have this function called last digit that does the computation. Okay, so let's look at the sieve, right? So sieve is actually nothing new here. I believe I just copy and pasted the same code and changed this to be a million. So it's exactly the same code as before. And then this find power, you give me n, then this will tell you the power for that prime in n factorial. So what do I do? Basically, this is pp is basically this prime power. Start with p, then p squared, p cubed, p to the fourth, and so on. And as long as n divided by the prime power is greater than 0, that's the number of multiples of p squared, p cubed, p to the fourth, and so on. As long as the number of multiples is greater than 0, I add it to the answer. I increase the power by 1. So it's p squared, p cubed, p fourth, etc. And then when I'm done, when basically this prime power is bigger than n, then this will be 0. And then whatever I manage to add up, that's my answer. So what do I do here in the last digit? So I compute the exponent for 2. I compute exponent for 5. Then I basically just get rid of the 5. And then the 2 is just the exponent of 2 minus the exponent for 5. And then I just multiply that into, so 2 to that power, put it into the running total and mod 10. And then for all the other primes, as long as it's not 2 and 5, I do the same thing. I find the power. If for some reason the exponent is 0, I'm done, because maybe the prime that I'm choosing is bigger than n. And then I just multiply that in. This power mod basically computes p to the e mod 10. So p to the, this is power mod, it's here. If you're asking me to raise something to exponent 0, I just return 1. If the exponent's odd, then I do the trick where I compute recursively the exponent minus 1, p to the k minus 1, and then times p, remembering to mod 10. And then if it's even, then this is the part where I do the divide and conquer. I basically half the exponent, I compute p to the k over 2, and then whatever result is I square it. So that's this is how you compute the last non-zero digits of n factorial. And the main, I guess the main lesson here is that a lot of times in number theory on problems that involves numbers, products and so on, you want to think about the prime factorization and asking yourself, if you know the prime factorization of the answer or whatever it is, does that help you? And if it does, then you have to say, well, okay, how do I get the prime factorization? And in the case of factorial, basically, because n factorial, it's just a product of all the numbers 1 through n in a regular way, then it's whatever you use to do SIF to find out, mark multiples of 2 and so on and so forth. It's exactly the way that you can use to factor these numbers as well. Okay, so that's factorization of n factorial. What do we think about this? Do you think you can try solving this problem?
Think so now. Yeah.
Probably.
Yeah, so I don't know if you have taken number theory, did you talk about the factorization of n factorial at all?
I don't remember doing that,
Yeah,
but
it might not, it's not a standard topic. Probably doesn't have a lot of applications, but in this case it's useful. Actually, the last day before the pandemic, with it closed the university, was March 14, 2020. And we had I gave a talk just before the university closed on that day about how to compute pi. What you can actually download these programs that computes pi quickly, and so I was talking about algorithms involved in that. And one of the tricks is to figure out how to factor n factorial, turns out, to make it fast to compute pi. Anyway, that's a different story. All right. Okay, last one. So you like your food hot. Okay, so the easiest thing to do is just explain what's going on, I guess. So you know that you made this much money, $725.85. The numbers that they're giving you, the total money that you made is always going to be less than or equal to $10,000, and always 2 decimal places. Okay, and then the individual things that you can sell potentially to get these profits, it says that the first type of thing that you sell can make you $1.71. The second one can make you $2.38. So knowing that you made a total of this much, how many of each did you sell? Okay, and if there's exactly one combination, so here, if you sell 199 of the first type, 162 of the second type, it works out to be this one. Here, the answer may not be unique. You made a total of $100. You have 2 types of things, one that sells for 20, one that sells for 10. So you could sell none of the first one, 10 of the second one, or 1 of the first one, 8 of the second one, and so on. So when there are multiple solutions, you're supposed to print all of them, starting with the one that has the fewest first type, and then list all of them. Also, there's a chance that there's no possible ways of making the total, no matter how much you sell each one, then you say none. The important thing is that you can only sell an integer number of something. You cannot say I'm selling half of something, because if you can do that, then it turns out that there's an infinite number of answers. Okay, so let's just basically, what are we looking at? You're given a total T. You're given 2 types. They call T1 and T2. And the question is the unknowns. It's, let's say, N1 and N2, and you're asked such that T is equal to N1 times T1 plus N2 times P2. Now, if N1 and N2 can be any number whatsoever, then you can just pick anything, doesn't matter, 7 times P1. And then you can always solve for P2 by saying something like T minus 7 P1 divided by P2, it's N2. But of course, this number may not be an integer. And that's one of the problems. The other thing is, so these two have to be integers, but not just any integers, must be greater than or equal to 0. Okay, you cannot sell a negative number of stuff. And that's why this problem is a little bit trickier than it looks, because of this constraint. If you didn't have these constraints, you have an infinite number of solutions. You can pick any N1 you want, basically pretty much any N1 you want, solve for N2, it will almost always work, provided P2 is not 0. Okay, so this doesn't work because everything's integer. And then what are the limits? The limits is T is up to $10,000, and then P1 and P2 are less than equal to $100, I believe. Okay, so Luke, you tried it a few times.
Yeah.
Okay. Do you want to share with people what you tried?
So I used the extended Euclid algorithm,
Okay.
and then so that'll give me no solutions or at least one solution. And then if I have one solution, then I go through and try to find multiple solutions. So I figured like I'd either have like either X would be positive or Y would be positive, or one of them would be negative. And then the one that was negative, does this kind of make sense what I'm saying?
It
Like
makes
if I
sense to
run-
me.
Okay.
It makes sense to me, but I don't know if it makes sense to anybody else.
So
But that's okay.
So if like Y was negative, then I have Y prime. So I recalculate X and Y prime for every iteration, and then I have like the formula for any solution. So like Y prime equals Y minus A over D times K. So I just keep calculating that until X prime is greater than 0.
And so what are you getting? Are you getting wrong answer? Are you getting time limit?
Yeah, I'm getting a wrong answer. So I passed the test cases, and then I switched everything to long because I tried a really large thing, and that seemed to change something. And then I still get wrong answer, so I'm not sure what. And then I got wrong answer for a while because I wasn't sorting it. So I put everything in a pair, and then I sorted that pair.
Mm-hmm.
So I'm not sure what I'm doing wrong right now.
Okay. So the first question, I guess, for other people might be, why are we doing extended Euclidean algorithm at all? And what is the extended Euclidean algorithm? So you are doing this because you have taken number theory and you know what this is about. Yes?
Yeah.
Right. If you have not taken number theory, then you probably don't really know why you want to do this. So let me backtrack for those people that might not have seen this. Oops, this whiteboard thing often crashes when I try to create a new page. Okay, so you are basically given T integer. So why do I say integer? Because you are going to convert all the decimal numbers into cents. Okay, so we're not gonna have floating point numbers. We're just gonna count cents. So if it's $10,000, there will be there's $10,000, then it will be 1 million cents. Okay, and same thing with P1 and P2, they will be up to this many cents. And the reason why I do this is because I don't have to worry about round off errors. Everything has integers. So we're looking for n1, n2 greater than or equal to 0 integers such that t is equal to n1 times p1 plus n2 times p2. And these are all integers. Everything here is an integer. And these are called linear Diophantine equations. Okay, so if you've taken number theory, you will of course you will for sure see this. Okay, Diophantine equation basically means that you're only interested in looking for integer solutions. Okay, and linear, well, linear means that you don't have product of the unknowns or n1 square, or things like that. It's not quadratic, cubic, or some other thing. Okay, so now I don't necessarily want to prove everything to you. If you really want to learn the proofs, I guess you can go look up this on the web, look up linear Diophantine equations. But how do you figure out whether there's solutions or not, and if there's solutions, what are the solutions? Step 1, compute the GCD of P1 and P2 and call it G. Okay, so the two numbers that you have, the two type of things that you have, compute the GCD. If T is not divisible by G, there's no solution at all. Okay. Now, when I say linear Diophantine equations, n1 and n2 are integers, but they can be negative. So we have to worry about that. But if the total, the right-hand side, well, the right-hand side, I wrote it on the left-hand side. Anyway, if the total is not divisible by the GCD of P1 and P2, there's no solution of any kind. You can stop right now. Okay. What if there's a solution? What if T is divisible by G? Well, then it's a little bit more complicated. Step 2. So if you use the extended Euclidean algorithm, you will get not just the GCD, but you have two multipliers, S and T, such that the GCD of P1 and P2 can be written as S times P1 plus T times P2. Okay, this is extended Euclidean algorithm. Okay. And remember, let me just rewrite it just right here again. The equation that I'm trying to solve is this one. 3, if you then take T divided by G, because we know that it's divisible, otherwise you would not have come to this stage, you would have set no solutions already, times S and called S0, then T0 is T over G times T, then basically S0 times P1 plus T0 times P2 is what? Well, you just substitute. It's T divided by G of S times P1 plus T times P2. And we know that S times P1 times T times P2 is G. And then, of course, the G cancels out, it's just T. So what's going on? So S0, okay, why am I writing so? Because that looks like S0. Thus, S0 and T0 is a solution for N1 and N2. Okay? But of course, this may not be, it may not be okay, because even though these are integers, it may be that N1 and N2, not both of them are positive. It could be that one of them is negative. but at least you got one solution. Okay, so this is the first part, to get any solution at all. And then the last part is, it turns out that if there's one solution, there's actually an infinite number of solutions. So all solutions are of the form, they always look the same, form S0 plus K times P2 over G, T0 minus K times P1 over G, where K is any integer. So you pick any integer K, plug in this formula, you'll get a solution. There's an infinite number of these solutions. And you basically take one of the solutions for S, then add some multiple of this P2 over G, and then the other one would be subtract some multiple of P1 over G. Even though this looks like a fraction, this is always evenly divisible because G is a common divisor of P1 and P2. So G must divide P1 and P2 properly. There's no fractions introduced. Okay, so that's where we're at. Now, Luke, is this kind of where we're at? Up to here, everything sounds about right?
Yeah.
Okay, so now, okay, let's try to add another page and hope that doesn't crash. Okay, good. So now let's go back to here. T0 minus K P1 over G. Now, what you need to do is you need to choose some K values of K to make it work. What does making it work mean? It means that both components are bigger than or equal to 0. Okay? So let's start, that doesn't really matter which one we start from. I think my solution actually will look slightly different because I do something slightly different, but it doesn't matter. Mathematically, it's the same thing. So I'm going to try to figure out what value of K should I put in so that these two are both bigger than or equal to 0. So how do I do this? Well, I just solve for K. So T0 is greater than or equal to K P1 over G. And then I can say T0 times G over P1, it's like this. And then over here, I do the same thing. S0, it's greater than or equal to minus K P2 over G. Then I say S0 times G over P2, do a negative sign. And now you have to be a little bit careful because when I move the negative sign, I also have to flip the inequality. Okay, are we okay so far? This is kind of maybe a little bit tricky, but this is, I don't know where you learn inequalities, maybe in high school somewhere. Anyway, so with this, you know that K has to be less than or equal to this, bigger than or equal to this. So then we just have to compute whatever this number is and whatever this number is, right? Now this number, it is possible that this is not an integer. So this could come out to be, I don't know, 8.47 or whatever. So if it's the case, then actually you want K to be an integer. So that means you want to round this down. And similarly, this may not be a positive, this may not be an integer, so you need to round it up. And whatever number comes out to be, that will tell you that K must be with a certain range. So maybe this comes out to be, I don't know, between 8 and -2. if that's the case, if you figure out that this is true, then all you have to do is go back to this formula and plug in k equals to -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, and that will be all your answers. And that's it. Now, Luke, where did your solution start to be different from mine?
Right here. So maybe I'll just change everything into like a for loop then, and just start at that one bound and go to the other bound.
Now, did you try to compute these bounds, or were you doing some sort of guessing?
I was doing something else. Yeah, I was just saying if
I mean,
the y.
you don't have to do it the way that I do. I mean, so the way that I do is sort of the most precise way of doing it. But you could also say, well, let's pick some value of k, right? You know that when whatever value of k here, if you pick a k, let's say you pick 0, this is negative.
Mhm.
What do? You pick a bigger k, right?
Yeah, that's what I did. Yeah.
And you can kind of just keep on playing this. I don't know if you even do a binary search and so on. But the problem, of course, is picking a bigger k here makes this thing smaller, right?
Yeah.
So there's probably a way you can do kind of a binary search, but you have to be a bit careful to maintain to worry about both bounds.
Yeah.
The way that I do it, it's kind of obvious which way it is, because it's just mathematically one single calculation. The only thing that you have to worry about is how do you compute this floor and ceiling. Okay, and this turned out to be not so easy if you don't want to use floating points. Okay, but before I go on, any questions from anybody about what I've written so far? Okay, so how do you compute, in general, A over B floor and A ceiling like this without using floating point numbers? Okay, so in C++, if I just write A/B, that's dividing and round it down and then getting rid of the fractions, yes? And if I want to round up, then the way to do it is actually add 1 less than the denominator and then divide by b. And that will round up. Provided a and b are greater than 0. If a and b, if one of them can be negative, then you got trouble. Because when a and b, any one of them or both are negative, then what these things provide, it's unknown. I think we talked about this before, right? I think I talked about, what is this? And the answer is I don't know, because C++ can give you some headaches depending on what it decides to do. It can give you -2, it can give you -1. So if one of these or both of these, if both of these are negative, I guess you can just get rid of both the negative signs on both and just pretend they're positive, no problem. But if one of them is negative, right? So if I have -5 divided by 3 and I want to do floor or minus or ceiling, well, what do? Well, you look at the number line. If this is 0, this is positive, and this is negative. If this is -5 over 3, so this is like -1.666. And if I flip it over, then the floor, if I do this, if I take the floor of this that's rounded down, that's actually the same thing as the positive one rounded up, and then you negate it. So what am I saying? What I'm saying is, if the number that you have is negative, you can pretend it's positive, round it in the other direction, in the opposite direction, and then negate the result. If you do that, then you don't have to worry about negative numbers screwing up your values, because you always make sure that you only do this rounding with positive numbers, with integers. But also, when you use these operations here, they are integer calculations only, you will know that you will never have to worry about round off errors, right? The worst thing that can happen is that you're trying to do this rounding things, rounding down or rounding up, but a over b is an exact integer. And then you say, well, you know, if this answer is supposed to be exactly 3.00, you hope that rounding up and rounding down would be 3. But if there's any kind of round off errors and you get 2.999, then rounding down can kill you. Or if you get 3.00001, then rounding up can kill you, right? So that's kind of where that is. Does that make sense?
Yeah.
So what is the main story? The main story is linear Diophantine equations. And it's a particular topic in number theory that's quite useful in computer science, because you quite often, you know, you might have multiple objects of different costs, and you need to know, you know, putting things together, adding them up. So this is almost, you can also think of this kind of like, almost like knapsack, right? You have a knapsack of a certain capacity, and you have two types of things with the different weights, and you want to know, or coin change or whatever, how many the different ways you can use these two objects to make the total capacity, or the coin changing problem. You have a total amount that you want to make. You have two types of coins. How many of each type of coin do you use? If your answer is either just yes or no, can you do it or can you not do it? You can actually just use the algorithms that the dynamic programming thing we talk about for coin changing. That would actually just work. No problem. But the reason why it doesn't just work in this problem is because you are asked to produce all solutions, not just yes or no. Okay, or not just one answer. If you're only producing one possible solution, actually, dynamic programming for coin changing algorithm will actually just work. You don't even have to do any of this number theory stuff. But the fact that you need to get all possible solutions, that's where you need the linear Diophantine equations, the theory, to understand what to do. Okay, so that's all of the problems this week. So I think this was actually, I guess, in some way a pretty successful set, because you all got something. It's not that you didn't get anything, and then it stretches you a little bit at the tail end, so you learn something new that you may not have learned before. So if you can go and finish that set, that would be great. And then next week, does anybody have any requests on what to look at?
Well, now that you mentioned knapsack, I haven't done much with knapsack, so that might not be bad.
Okay. Maybe I'll throw in a knapsack somewhere, but I don't think I want to make knapsack problem set, because we've done that a few times now. But I can throw in one problem that's knapsack.
Sounds good.
Anything else?
Maybe something with like graphs or something.
I can do that. I think earlier in the summer we did shortest path and minimum spanning trees. So I can pick some other graph problems, yes, that you may or may not have seen before. Sounds good?
Yeah.
Okay. Anything else? Okay. Well, I guess it's just the three of you that are regular showing up now. Let me stop the recording.